Hi, my name is Josephine Nwama, and this is Lab 2, Motion of a Falling Object. So the purpose of this investigation is to observe an object's position as it's falling through an experimental model using the tracker platform and compare it to two predicted computational models of its position, considering solely gravity and then considering drag and gravity together. So our system is a ball, and the surrounding is everything else, including drag, or air resistance, and gravitational force on the Earth. So here's a brief overview of the main results. So some fundamental principles we need to understand is Newton's second law. The net force applied onto a system equals the change in momentum over the change in time. And when we look at that as an equation, we can derive the velocity update formula, which will allow us to see it as the velocity changes on our computational models. And then we can also get our position update formula. Now, for these two models, we're considering gravity and then gravity plus drag. So F net is the sum of the forces on the system. So when we're solely considering gravity, F net equals the force of gravity on Earth, which is negative mg y hat, with g being 9.8 meters per second squared, which is the acceleration on Earth. And then when we're considering gravity plus drag, our F net is, again, the force of gravity plus the force of drag. And then up here, you can see, again, the equations for them. So another fundamental principle we need to get our head around is terminal velocity, which is when the force of drag pointing in the y hat direction is exactly balanced to the force of gravity pointing in the downward, or I guess negative y hat direction. At this point, drag is equal to the weight of the object, so this means the object is now falling at constant velocity because F net equals 0 and the object no longer has acceleration. And as you can see here with our force body diagrams, as time progresses, the force of drag increases, and then it becomes equal to the force of gravity, and then this is going to make F net 0 and give us constant velocity. So our experimental method is recording a video of a ball falling, recording its position on tracker, and then finding some data that we can use to edit our Glowscript code, and then make our predicted models and compare the data. So some assumptions we're making is that the ball is dropped in a straight line, and solely the y direction coordinates are changing, but x and z direction coordinates are constant. So here's a video of tracker and me tracking the ball. So here's some data from tracker. The total time from when it left my hand was 0.467 seconds. The initial position was basically 0 in all coordinates meters. And then the initial velocity was 0 meters per second because it was at rest before it left my hand. So we can use that data for our computational model. We'll start with the one for gravity. The mass of the object was 0.142 kilograms. We added our initial position and our initial velocity, and our change in time, which was 1 over 30 seconds, because that was the frames per second. And so in this case, we're using our F net equals solely Fg, because gravity is the only thing we're considering. And that's what we have here. Additionally, we added the velocity update formula and then the position update formula, which were all explained earlier. We did the same exact thing for the computational model for gravity and drag, except that for Fnet, we have Fg plus Fd, which can be seen over here, and Fd involves the coefficient of air resistance, which is seen as B, and B equals 0.0865. So here we're comparing the models. As you can see, the observed model is closer to the computational model of gravity plus drag than solely gravity. This is because gravity plus drag includes all the things, majority of the forces in the real world that would be affecting the ball as it's falling, while gravity solely is the acceleration downwards. So some possible sources of error would be estimating the correct points for tracking, other forces being involved, contact force from my hand, the ball not being dropped straight and not being able to map accurate coordinates, and calculation errors. So let's have some discussion questions. So which model predicts a terminal velocity? On this side, this is the velocity versus time graph for solely gravity. It's pretty much constant and pretty linear. So for our gravity versus drag, velocity versus time graph, you can see that at first it is going down faster due to the change in velocity being quicker or steeper, and then it's going to become more linear over time, which is what we explained with our free body diagrams, that as it's becoming more linear as time is passing, the Fd magnitude is becoming almost equal to the Fg magnitude, which will make it have constant velocity. Our last discussion question is, would the terminal velocity be the same or different in the case that from when it was initially dropped from rest versus if it was initially thrown downward? And it would reach the same terminal velocity, however it would take this different amount of time. The graphs would be the same slopes, However, it would just take a different amount of time for the magnitude of drag and the magnitude of gravity to be equal. Thanks, and here are the links.